Hello. Welcome to my channel. In this video we are going to solve exercises using what we have learned about parallel lines cut by a transversal. In the first exercise there is a trapezoid ABCD. And we draw the segment EF. That is the segment between the two midpoints of the oblique sides. We want to prove that the midpoints of the two diagonals of the trapezoid lie on the segment EF. So we write that AM is equal to MC, and BN is equal to ND, where M and N are the intersection points between EF and the two diagonals. We start by proving that AM is equal to MC. If we consider the two triangles, ADC, blue in figure, and AEM, yellow in figure, we can prove that they are two similar triangles. In fact, it's obvious that the angles EAM and DAC, green in figure, are congruent. Then, if we extend the side EF and DC, these are two parallel lines cut by the transversal AD. And it's clear now that the two angles, AEM and ADC, red in figure, are corresponding angles, therefore congruent angles. On the other hand, the diagonal itself is a transversal that cut the two parallel lines. So even the two angles AME and ACD, yellow in figure, are congruent, being corresponding angles. So the two triangles AEM and ADC have the corresponding angles that are congruent. Therefore they are similar triangles. A property of the similar triangles is the fact that the corresponding sides are proportional. Knowing that AD is 2 times AE, we know that the proportionality factor is 2. So we can state that AC is 2 times AM. And from this it follows that AM is congruent to MC. We have proven in this way that M, the intersection point between EF and the diagonal AC, is the midpoint of the diagonal itself. To prove the same thing for the point N, we can proceed in a similar way with the triangles BDC and BNF. I'll leave it up to you to do it in detail. And we move to the second exercise. We have a segment AB. We draw two parallel lines. One that passes through A and the other that passes through B. We draw the bisectors of the four angles, alpha, beta, gamma and delta in figure, formed by the intersection between the segment AB and the two parallel lines. If we call P and Q the points of intersections between the bisectors, we want to prove that APBQ is a rectangle. The straight line that lies on the same direction of the segment AB is a transversal that cuts our two parallel lines. And it is evident that alpha and delta are alternative interior angles. And so they are beta and gamma. We can therefore state that delta is congruent to alpha, and gamma is congruent to beta. Being AP the bisector of the angle alpha, we know that the angle PAB, orange in figure, is equal to 1/2 of alpha. For the same reason, the angle PBA, red in figure, is equal to 1/2 of beta. If we consider the triangle APB, the sum of the internal angles is equal to 180 degrees. At this point we know that the angle APB is equal to 180 degrees minus PAB minus PBA. Then we proceed in a similar way with the triangle AQB. Here we know that QAB is equal to 1/2 of beta and QBA is equal to 1/2 of alpha. Therefore we obtain the value of AQB. That is equal to APB. We have proven that a pair of opposite angles of the quadrilateral are congruent. If we can prove that even the other two opposite angles are congruent, we can state that the quadrilateral is a parallelogram. We start with the angle PAQ. That is equal to the sum of PAB, orange in figure, and QAB. Blue in figure. Therefore it is equal to 1/2 of alpha plus 1/2 of beta. But we can immediately see that even PBQ is equal to 1/2 of alpha plus 1/2 of beta. To prove that our parallelogram is a rectangle, we have to show that all four angles are congruent. In fact, the rectangle is a particular kind of parallelogram with four right angles. We can trivially show that each of our angle measures 90 degrees. It is evident from the figure that alpha and beta are supplementary angles, so their half sum is 90 degrees. And of course even 180 degrees minus their half sum. So we have proven that the four angles of the quadrilateral are right angles. Therefore it is a rectangle. One last thing about this exercise. We ask ourselves what happens if the two parallel lines are perpendicular to the segment AB. In this case, each of the four angles formed by the intersection between the segment and the two parallel lines is a right angle. Furthermore, we know that PAB, PBA, QAB and QBA are four congruent angles that measure 45 degrees. This implies that APB and AQB are two congruent isosceles triangles, having the base AB in common and the two base angles that measure 45 degrees. And this means that all four oblique sides of the two triangles are congruent. Therefore in this case our quadrilateral APBQ is a square. Well, this video is over. If you like my videos, you can subscribe to the channel. See you soon with another video. Bye.